Hi everyone, welcome to this new lecture of hydraulic machines. In this lecture, we'll discuss about the velocity triangles and work done on inward radial flow reaction turbine. In our last lecture, we have discussed the theory part of this inward radial flow reaction turbine. And in this lecture, we'll draw the velocity triangles and we'll find out the work done on inward flow reaction turbine. So this diagram you can see, this is of inward radial flow reaction turbine, and in this we can see the water used to come out from the outside to inside. That's why it is called inward radial flow reaction turbine, and the water is moving here with radially. So actually this is the diagram what you can see. In this, actually if you see another one, casing will be there. So at the outer part here it is, casing will be there, and the water will be comes out from outside. If I draw like this, then suppose like this will be there, and through this casing, or you can say this is the penstock or pipe which is which came from the dam. So through this the water is to come inside actually. Okay, and slowly the water is to move throughout this casing, and it is to move to this runner through the guide vanes. So this is actually, these are the guide vanes. These are the guide vanes what you can see at the outer periphery of the turbine. Okay, these are the lines what you can see here. These are actually guide vanes, and these guide vanes are fixed on a wheel. That is, you can see the outer wheel of this, or you can say the guide wheels. So the water which is coming from outside, and it will goes through this turbine through this guide vanes. Okay, through this guide vanes the water will goes inside. So this will act as a direction, flow direction of the water. And after coming after coming inside, then you can see a runner is there, and this is actually moving vanes are here. So this is also called as runner, and number of blades we can see which are fixed on this. So this is actually moving, these are moving vanes, and which are fixed on a runner. So when the water coming from outside, if you see, now you try to see the direction of this water which came from outside. So the outside water, when it is trying to come inside, so it will be strikes over here at this point, and it is to go out from here. Okay, similarly if the water is coming from outside, then it will strike here and it will go outside. So what I mean to say here, that means the outer periphery or outer diameter, you can see this one. If I consider this one, this is the outer diameter of the runner, and you can see this is the diameter one, d1 is given. Okay, d1, which is the nothing but the outer diameter. And similarly, when the water flows over these vanes and it is to goes out from here, so this one we can consider this is the inner diameter of the runner, and the runner is fitted on the shaft. This is the shaft part is there, what we can see here, this one. So the shaft will be connected to the generator, and when it started rotating, then the shaft will be started rotating, and it will be generate the electricity which is connected to the generator. Anyway, so this is the concept of like water will be come from outside and it is to goes inside, and how it is going inside, that I have shown here. So what I told you, that we'll draw the velocity triangles and we'll find out what is the work done on inward radial flow reaction turbine. Actually this concept already we have discussed in our previous lectures, when we have discussed that number of blades are fixed on a wheel. So if you see this diagram, I hope you remember the previous what we have discussed. So these things already we have derived and discussed in our previous lecture. So here I'll just give a small hint, or so just give a small brief about this, how to find out the work done. Okay, so as you can see, as I told you, that water striking here at the inlet of this, that means the outlet, the outer diameter of this runner is the inlet of the wheel, inlet of the water, and the inner diameter of the runner is the outlet of the water outlet, or we can say the exit of water. So now this diagram actually I have taken like from the previous lecture where we have discussed about the force and how to find out the work done and the power. eh. So here we can see that if I draw this one, so this is the wheel is there, and if you extend the wheel diameter, it can be like this. It may be more, little bit more, because center point is given here, and similarly this will be also a larger diameter of a wheel, and the blades are fixed on this diameter of the wheel at this point, you can see. So this one, the blade, okay, number of blades are fixed on the wheel. The same thing I have shown you, the number of blades are fixed on a wheel, that is guide vanes or guide wheels, we can say. So the water is coming and striking at this point, you can see, as I told you, the water coming here and is striking at this point at any one end of the blades. So the water, when it is striking out the blade at the velocity of v1, okay, at the velocity of v1, and it's this is actually absolute velocity you can consider, or you can consider the velocity of z. So that is v1. This is v1, and next is, though it is acting on this blade with an angle of alpha, so this alpha actually, this is called guide blade angle. This alpha is called guide blade angle, which we can see, which makes an angle of this velocity with respect to the direction of blade, because after striking here, the blade started moving in this direction. So if I consider this is the direction of the blade in this direction, so this makes an angle of alpha here. So first one, what you have seen, v1. v1 is nothing but, I already told you previously, velocity of jet, or we can consider absolute velocity of jet. Now similarly, alpha. Alpha is the angle between this velocity of jet and with the direction of motion. So that is nothing but guide blade angle actually. This is called guide blade angle. Similarly, if I will resolve this velocity in respect to x component and y component, then I'll get, this is wheel velocity. This is wheel velocity, that is vw1, and this is flow velocity vf1. Velocity component like vertical component, and this is horizontal component. So, and see, when there is a discussion of like two velocities or two objects are moving in the same direction and the opposite direction also, there we need to consider the relative velocity. So vw1 came and this is vf1 came. This, all these things we are considering in the inlet condition. At the inlet condition we are considering. And next one, as I told you, that vr1. So vr1 is nothing but the relative velocity of the fluid, we can say, with respect to the plate. So relative velocity will be at here, and that will make an angle of theta. Okay, this is vr1. Now again one more terminology came, that is theta. So theta equal to what? Theta equal to vane angle. This one is the relative velocity with respect to the direction of this blade. So this is actually vane angle. So this diagram actually the inlet diagram, the inlet velocity triangle for the blade when it is mounted on a wheel. Okay, similarly, if you see the outlet triangle, so outlet triangle will be, and this is the tangent part actually. This is the tangent part of this point. Similarly, we can draw another one tangent at the outlet condition, and the velocity of this one just will become in the reverse way. Like if I take a blade here, so just I'll take a blade here, and yeah, just to give it, and this is the tangent of this one, and the inlet of the velocity, as I told you, that the water strikes the blade at this point with a velocity of v1, and this is the component of this x component of this velocity, which can be marked as vw1, and the y component is this one vf1, which is nothing but flow velocity, and this makes an angle of alpha here. And next is a relative velocity here, this is vr1, which makes an angle of theta, and this distance is nothing but u1. U is nothing but, one more terminology here, u. So E1 I can give it here. That is the tangential velocity, I can say. This is the tangential velocity because it's, you can consider in this direction. So which strikes the blade tangentially, you can say, or even we can say the peripheral velocity also we used to call that one, or used to call the, it is also velocity of the vane. Velocity of the vane is to consider the U, though it is considered the inlet condition, we can say it is a like vane velocity or wheel velocity, tangential velocity of the wheel at the inlet condition. And similarly, as we are discussing about the outlet one, when the fluid is coming out from here and it is to go out like this, okay, and the triangle will be like this. And here it will be slightly different, though the velocity of fluid, this absolute velocity that will come out from here at the outlet condition at this point, this is V2, and it makes an angle of alpha here. So at the opposite side, it will make an angle of beta here. Okay, and what is the length with respect to this one? This is VW1. So here it will be like VF2 vertical component of this V, and this is our horizontal component of this V2. That will be nothing but VW2, and the direction will be like this. So the direction will be like this. Similarly, the relative velocity which came here with respect to theta here, that will come out from this at the outlet condition here, and this one we can give VR2, and that makes an angle of phi here. Okay, that makes an angle of phi here, and the velocity will be given here. This is U2. This is U2. Here you can see U1 is given after distance here, and here it will be U2. Yeah. So this is the velocity triangle for at inlet condition. This is at the inlet condition, and this is at the outlet condition. If you want to see more details about this, you can see, you can refer to our previous lecture where we have discussed these things. So as I told you that we will find out the force and the work done. For this, let's start here. So first one, I'll find out the mass of water. The mass of water striking per second. The mass of water striking per second for a number of vanes, for a series of vanes. So that is nothing but we can write, this formula is nothing but we can write, this is rho A V1 at the inlet condition. So here A equal to area of jet and V1 equal to velocity of jet. So this is the mass of water striking per second for number of vanes, same thing. Now, though with the impact of this striking, it creates a momentum here. Now you can see, though it is, it is attached in a wheel, so it started moving. And this outer diameter D1 and inner diameter D2. So it is given with a radius of, this is R2, and this is R1 and R2. R1 is the outer one, R2 is the inner one. Okay, these are the radiuses. So now we'll find out the momentum. The next one is the momentum of water, which is striking the vanes in the tangential direction. In the tangential direction at inlet condition. So this one we can write, what is the momentum? The mass into velocity. So mass into velocity, as I told you, tangential direction, what is the velocity will be there? That means we need to consider the velocity of in the horizontal direction, tangential direction, this one. So what is the velocity mass here? That is rho A V1 into, we can write, this is VW1. VW1 is what? The VW1 is the component of velocity V1. Component of velocity V1 in the tangential direction or in the horizontal direction. So this VW1 also we can write, this can be written here like V1, this is cos alpha. V1 cos alpha also we can write. Similarly, we can find out the momentum of water striking tangentially at outlet condition. Just I'll go for here briefly. I won't go to the depth here because already we previously have discussed. I'll give a hint on this. So this will be like rho A V1, and the see the mass here, we need to consider a few assumptions are there, like VR1 it will be VR2, and like V1 equal to V2. So these are some assumptions we need to consider. Here we can write this is the mass of water which is striking into VW2. So VW2 actually we need to consider the component of velocity V2, the component of velocity V2 at the outlet condition. So that is nothing but what will be the component of velocity here. So that we need to consider it here. But here the velocity is this one. So the component of velocity is this one. That means V2 cos beta. V2 cos beta, but it is coming in the reverse direction. The total is VR2 cos phi. But here we are considering only this one. So here what I can write here, this one I can write, this is rho a V1 into this is minus V2 cos beta. This one, this is V2, and the component is like horizontal component is VW2, though it is coming in the reverse direction. I need to consider this a minus. So we can write here minus of rho a V1 into VW2. Okay, and here V2 cos beta I can write VW2. That's one. This one. As I told you, this is negative symbol is taken for the opposite direction of the flow. Now, momentum calculated. Now we need to consider the angular momentum. We need to find out the angular momentum per second at inlet condition and outlet condition. Per second at inlet condition equal to what is the angular momentum will be there? That is nothing but momentum what we have calculated, momentum into the radius at the outlet condition. Outlet condition radius is nothing but R1. So what we can write here? So this can be written like rho a V1 into VW1 into R1. Okay, so this is the angular momentum per second at inlet condition. Now similarly we can find out the angular momentum per second at outlet condition. At outlet condition equal to similar things, momentum into momentum of outlet into the radius of outlet. Outlet is this one, inlet is this one. Water is entering here, that's why it is inlet. Water is existing here, that's why it is outlet. So here also we can write this is minus of rho a. Here we can write V1 into this is VW2 into this is R2. Okay, this is angular momentum per second in inlet and outlet condition. Now, if you want to find out force, here force will be not there, we will consider the torque. So torque is nothing but we can write force into the distance. So here let me write the torque exerted by the water on the wheel. So that is nothing but torque equal to, we can write the rate of change of momentum. This is nothing but rate of change of angular momentum, not momentum. This is rate of change of angular momentum. This is nothing but rate of change of angular momentum. So we have calculated already inlet angular momentum, outlet angular momentum. So this can be written, what is the inlet one? This is rho a V1 into VW1 into R1 minus my rate of change of momentum is like initial angular momentum per second minus final angular momentum per second. So in initial momentum, angular momentum is this one at inlet condition, minus the final one is this one, we can write minus of this is rho a V1 and this is VW2 into R2 into R2. So here we can write this is, we can take a common of like rho a, this is V1 and here bracket start, we can write this is VW1 into R1 and minus minus plus, we can write this is VW2, this is R2, and here we can close the bracket. Now similarly, torque we have calculated. As I told you that here force on behalf of force, we can calculate the torque. Now we need to find out the final work done. We need to find out the work done per second, work done per second on the wheel. So this one equal to, we can write like torque into the angular velocity. So angular velocity here, previously what we used to write to find out the work done, we used to calculate by force into distance. If it is work done per second, then distance per second, that is velocity. We used to calculate how it is, like work done equal to, we used to write previously, if you see, that is force into distance. Again, work done per second, if you write, then here also you can write distance per second. So this is nothing but we used to write force into, this is velocity. We used to calculate like this. But here, as we have seen, work done per second, we need to write like torque into angular velocity. So angular velocity equal to what? Angular velocity equal to omega. Okay, and we know that omega equal to, this is u/r1. So we can write omega actually, not u/r1, u equal to, or u1 equal to the peripheral velocity, we used to calculate omega r1. Similarly, u2 equal to omega r2, angular velocity into the radius as a outlet one, this is inlet one. So here we can put the value of this torque. What is the value? Like rho a v1, and this bracket start, we can write this is v w1 and r1, this is plus, here we can write v w2 r2, and bracket close into omega. Okay, so we can write, we can take this omega inside. So what we can write here, like rho a v1 bracket start, and this is v w1, and here we can write vw1 r1 is there. Let me write vw1 omega into r1. So if you see omega into r1, I can write directly u1 here. Similarly, omega into r2, so there also you can write vw2, this is u2. What I have done, omega into r2 u2, omega into r1 u1, that's why I have written. This is the final one. Now this is the work done actually. This is the work done per second on the wheel. This is our required answer. Now these things actually what we got here, when the beta is less than 90 degree. This one we got the condition when the beta is 90 degree acute angle. Now sometimes the beta will be like, if you see here beta is 90 degrees, less than 90. Sometimes the beta will be 90 degree, sometimes beta will be more than 90 degree. So at that condition, like how to find out? So a simple one. So when beta will be more than 90, when the beta angle is more than 90 degree, in that condition the work done will be, just you will need to consider the negative symbol of that. That means nothing but v rho a v1, this is bracket start, v w1 e1 minus, we'll get here v w2 u2, this much. So by considering this equation and the previous equation, the general expression we can give a general expression or equation for work done per second equal to, general expression for work done per second equal to, so you can write this is rho a v1 bracket start, this is v w1 e1 plus minus v w2 u2. This is our normal or general equation. When the beta will be 90 degree, this portion will be 0, only this part will be there. So this is the thing what we have discussed in our previous previous lecture also we have discussed. But now the concept came like how to find out the efficiency from this. And as I told you that this is the up to this we have calculated. Okay, up to this we have calculated in our previous topic. So this one some equation we can provide here. Give some equation number 2, then we can give equation number 2, and somewhere we can give equation number 1 like this. Okay, let's see how here. First one, let's give equation 1. This is equation 2. Okay, and similarly this is equation 3, and angular momentum equation 4. This is outlet equation 5, change torque equation 6, and this is 7, equation 7, and this is equation 8, and finally this one we can give equation 1. So up to here now we have now clear. Now this equation, what you can see here, we can write another one terminology that I can write here. Again, this term I can write on behalf of AV, I can write Q. AV1 V1 I can write Q, or Q1 I can write. There is no difference in this. So here this one we can write VW1 U1, and this is plus minus VW2, this is U2. You can close the bracket, and this one we can write equation 10. So this equation actually it represents the energy transfer per second to the runner. Now here VW1, VW2, these things already I told you, like field velocities and at inlet condition, at outlet condition, and E1 is the tangential velocity at inlet condition that can be calculated by like pi dn by 60. And here D1 is the diameter at outlet condition, and D1 is the diameter at the inlet condition. Like outlet for the wheel, but inlet for the flow or water, you can say. And similarly U2 we can write, this is pi D2 n by 60. This is the formula. This is inner diameter, this is outer diameter, and n is the speed. So here we can write, this is n equal to speed of turbine, which can be written in RPM. And now for this condition, if I will find out work done, I have calculated. Next one, if you want to calculate the work done per second, per unit weight of water, per unit weight of water per second. Sometimes the questions will be given in the problem like to find out in this terminology. So we can also calculate for this work done per second per unit weight of water per second. This is nothing but what I can write, like work done per second already you have calculated. And similarly next one is the weight of water, that weight of water striking per second, weight of water which is striking per second. Okay, now these things we can write like this equal to we can write, this is our equation what we got here, rho q, this one VW1 U1, and this is plus minus VW2 U2, bracket close, and the denominator what is given, weight of water, that one we can write actually this terminology as W equal to, I can write mg. Okay, so m part we can write rho into V into G, but weight of water per second is given in per second. Here also I'll write, and here also I'll write per second. Now volume per second, this is Q. So here we can write rho Qg. So here also I write rho Qg. So this one I can cancel rho Q, and what I'll get here, 1 by G bracket start. This is VW1 U1 plus minus VW2 U2, here bracket close. Now this is another one equation. This is like not a different one, just I have expanded that equation, the work done equation, or in terms of like work done per second per unit weight of water per second. So this equation actually represents the energy transfer per unit weight to the runner. Okay, and this equation actually also called as Euler's equation. This equation also called as Euler's equation of hydrodynamics machine. Euler's equation of hydrodynamics machine. And this is also known as the fundamental equation of hydrodynamic machines. Anyway, this is the equation. Now here, if beta is 90 degree, then this terminology is 0 and we will get only this equation. Now similarly, if I can find out the hydraulic efficiency. So hydraulic efficiency can be written like we know that runner power by water power. So runner power is nothing but you can write this one weight by 1000 G. The work done what we got, that also can be written plus minus this is VW2 U2 and divided by, we can write this is W into H by 1000. This also can be written. Now here we can cancel this W 1000, all the things will be cancelled here. So remaining part we can write like VW1 U1 plus minus VW2 U2 divided by this G part will come down. So we can write here GH. And this is another one equation where you can give equation number 12. And as I told you that runner power to the water power, and this is this power will be delivered, the power delivered to the runner, and this is water power. Now here, if the conditions will be given that the discharge is radial, the discharge is radial at outlet condition, then we need to consider VW2 equal to 0. Radial condition outlet means it will become straight line, so there will be it will be not axial one, radial one is there. So here what we'll get, this will be 0 means we can write this is efficiency equal to, this part is 0, so only we can write this is VW1 E1 by GH. So this is our efficiency formula. Though the equation is slightly lengthy and it will take some time to understand also, you won't get directly the concept. You can see one by one terminology from starting to last, it definitely you can understand. If you're having some doubt regarding this terminologies, you can refer to my previous video where I have explained in more details only about the this impact of jets on the number of vanes when it is mounted on a wheel. So I hope you understand. Still, if you are having doubt, you can give a comment in the comment box. Thank you all.